Okay, hi everyone. I think we can start. So it's our pleasure to have Ralf Metzler here with us. He's a chair professor of theoretical physics at Potsdam University. He did his undergrad and grad Ulm University and then postdoc at Tel Aviv University. He won numerous awards and focuses on non-equilibrium statistics, statistical physics, soft matter, theoretical biological physics, as well as physically motivated data science. So please, Ralf.
Thank you. Welcome, everyone. I had heavy lunch, so I know what you might be like. I will not come to you if you not offer something. Also, let's keep it informal. If you have a question, please ask just in the middle. Don't worry. So I apologize, it's very faint, but every talk of mine starts with a painting by Turner. And he didn't paint anything in Tübingen, but if I were telling you this is Tübingen, you would all believe me. At least it's the same river, it's a bit downstream, this is Heilbronn. So there he stopped and painted. But good. So what we do in my group, can I get rid of this thing at the top?
Yeah, what do we do now? It should disappear.
No, if you move,
I think what mine is.
This one? No, just doesn't work. You
can try to drag them out of the screen.
Oh.
Yes.
Sorry. So what we do in my group is a lot connected to stochastic processing, and it's typically also inspired by data. So I will show you real experimental data. I will motivate with data. And things that we're looking at would be connected typically to single particle tracking experiments. So what you see here, this is fantasy blue cloud. This is more or less the nucleus of a living cell. And these are experiments from Yuval Garini, just from Bar-Ilan University to Technion. And here you see little trajectories of the end parts of chromosomes of a living human cell. So that's kind of state of the art. What you see here, these are trajectories of proteins moving in cellular membranes. So this is kind of state of the art of experiments, beautiful stuff, lots of data that we have to understand. And as the resolution is getting better and better, we also see more and more complex behaviors that we try to understand. And a lot turns out to be what I want to call anomalous diffusion, departures from Brownian motion, from normal diffusion. So we saw it. And typically, physicists will like T to the alpha, where alpha is this anomalous scaling exponent. And if you want to relate it to the first exponent we heard before, it's just alpha over 2. So normal diffusion, alpha equals 1, H is 1 half. And then we look at effects like non-Gaussianity, for instance, here where the kurtosis differs from a Gaussian value. We look at whether processes are ergodic or not in a very simple practical definition. Whether a long time average of some statistical observable converges to the ensemble average or not. Or we consider processes that are aging, where the measurements, the result, when you evaluate your data, actually depends explicitly on the measurement time, for instance. And these are two Physics Today articles that you can check. This is relatively simple descriptions of that stuff. Let's be motivated. Today I want to talk specifically about long-range processes, fractional Brownian motion we heard about. And here I have a long list of all kinds of different experiments. That's a paper that we published with Miki Assad from Jerusalem last year. And this is an analysis of single particle tracking data according to 3 scaling exponents that were introduced by Mandelbrot. So they are about long-range correlations. This is just an exponent. This is what we will focus on. And then you have extreme events. And we have, this is the Noah exponent. Then we have no extreme events. What is the third one? Moses exponent, AJ, of course. Moses must be AJ. And you see all the blue numbers, they show you processes that are either positively or negatively long-range correlate. So we have data for single molecules in more or less water We have colloidal particles, micron-sized particles in cells. We have single-cell brooding ants, and then all kinds of birds. And the type of data you can see here, this is, for instance, a vulture that starts somewhere in the north of Israel, goes to the sea line, goes all the way down to the Red Sea and so on. And also in Potsdam, where I am, we have good connections to people following animals. And it turns out that these animals are very persistent in their motion. And of course, we expect it for an animal. They know where they want to go. They just, for instance, this guy just flies along the coast. Very few turning points until they come and, get food or whatever written. So you see, out of all these processes we have here, we just looked at them because we got the data. We didn't select them for the effect. But you see that there's a lot of blue. So these long-range correlations really play a role. Now, typically, when we look at experiments, the first indicator that we advocate and people analyze is displacement correlation, or if you want velocity correlation. For a normal random walk, it should ideally look like this. So we have a bin time. We look at certain, we compile the data according to certain bins, and within the bin time, our correlation of direction goes from 1 to 0. And then it's completely flat. That's what we know from a normal random walk. But these long-range correlated processes, they typically go for subdiffuse anti-correlated processes. They go to negative values, and then they have very slow power law recovery. So that's very typical for these systems. We see it here in artificial solutions. This is where, like micellar solutions, data by the inequality. This is about the slides where we use polymeric solutions. And these are examples where you have the same behavior in living cells, again, from the Correlated in Copenhagen. It's coupled with anomalous diffusion, typically exponents of alpha equals 3/4, something like that. Okay, you also see here, when you increase the bin time, the minimum is slowly receding. The depth is getting smaller. So this is an indication here on these time scales, you have a slow recovery to Brownian motion. So you lose the long range correlation when you go to bins. Here you don't have the effect. These are relatively short trajectories in bacteria cells. You see here for all the bins, it's more or less the same depth. You get the equal master curve, where they go from 1 second to 1 minute time series. You see again the effect that it's receding. And these are very beautiful experiments at the bottom from US Savants to petabytes. You can see the bottom. Okay. I'm citing all the good papers down here. Giving credit to the friends. Okay. If you send me an email, I gladly send you a link. You get all the slides with all the paper reference. That's what I can do. Let's look at fractional Brownian motion. We saw it several times already. From a more physical point of view, anti-correlations can be understood roughly, for instance, by looking at a polymer chain. So I have beads of a given mass, and then they're connected by harmonic springs, and they're all experiencing friction, of course, and independent noise. And for instance, when this particle here gets a kick to the right, you see that immediately it's being pushed back by the adjacent monomers. Then, of course, the disturbance travels the chain up and down again, and this actually affects these anti-correlations, right? I mean, you're being pushed here, then you're being pushed back immediately. That's what also Ralf said. One step is most likely followed by a step in the opposite direction. And one can show that when you sum up all these disturbances, so your characteristic times and the amplitude scale, you get more or less a power law, an inverse power law, memory indeed. Now, this is typically formulated with a temperature, but we are looking at systems now, fractional Brownian motion, when we are not connected to a thermostat, so that's in Klimantovich sense, for instance, open systems where we consider the noise independent. Then we get to this Najma equation. I know mathematicians don't like it, but physicists always put the PT on the left-hand side. I'm sorry, I'm a physicist. And we have these definitions that Gleb already showed us, and I'm using here this way of writing the noise with this smoothing parameter that was introduced by Mandelbrot. And if we go to sufficiently long times, we have this long range curve. This is long range correlations. Then we can calculate the displacement correlator, and what we saw already is one for negative, for anti-persistence, it gives the negative values, goes back. And one characteristic property I will come back to is that the area under this correlator for subdiffusion is exactly zero. Once you mess up with this, you will have convergence to normal diffusion. Look at what happens for a regular random walk. That's the one curve. I don't ask you for the color. It's the one going down to 1 here to 1 0, and then it's 0. And once you get positive correlations, you get curves like this. And when I look at actual, oh no, sorry, one little caveat at this point, and this is great. This is stuff that I'm discussing with Matthias Weiss at the moment. The full line here is exactly fractional Brownian motion, the model, but the data you see is actually diffusion of a particle on a critical percolation path. There also on many scales, you know, a particle tries to move one way, it gets stuck, it can only return. So this induces extremely similar anticorrelations. So that's already teaching us we need to look at more than just this velocity correlation. Good. Here I have one more example from the experiments. This is from Metzler's lab, and they analyzed several years ago. These are very complicated amoeba cells, and then they look at the motion of little vesicles in this amoeba cell. I don't show films, so if you watch these experimental recordings and you look at from the top at the cells, they're swirling. It's really shuffling everything inside in a circular fashion. So there's active motion, and this affects superdiffusion when the alpha is actually relatively high. It's about 3.5. But now all these experimentalists, especially the closer you get to biology, they like to poison the cells. So they use different kinds of poison, and when they use blebistatin, they inhibit the motion of the molecular motors. So everything stops, and the motion becomes extremely subdiffuse with an alpha around 0.2. So that's what they see in the experiment. This is the correlator for alpha 0.2, that's passive, and then these cells are very nasty. They recover, so they measure again after given time steps, and you see that all of a sudden you have your positive correlations. We cannot say with confidence that this is persistent fractional Brownian motion because we don't have the same handle on the process. We looked at it, of course, with a power spectrum, so we have indicators that it is still fractional Brownian motion, but we don't have, for instance, a control like area under the curve is zero. So this is quickly a recap to what Gleb showed us about the power spectrum. The only thing I want to flash up here is when you look at these distributions of amplitudes of individual power spectra for individual trajectories, they're stochastic, so they fluctuate in amplitude, and we can calculate the amplitude distribution here in 1 and 2 dimensions. The red one is always 2 dimensions, and the blue, that's also Gleb showed, that's the 1 dimension. And it's extremely sensitive. So here we have these vacuoles I'm talking about, and they are super diffusive, but when you look at the 2-dimensional distributions after here, and when you look at the data, it's actually meaningful because locally on small scales, there's an anti-persistence. So locally, they're zigzagging, and globally, they're really super. So this I can actually pick up this behavior. Let me skip this because we saw this in next. Let me continue with some examples. So now we go to our simulations. There we have a bigger control. We can follow individual particles from the simulated trajectories. These are different examples for model membranes. Model membranes consist of these long kind of V-shaped molecules. They have 2 tails and 1 head group, and they self-assemble when you expose them with water into a double layer. So this is when they're all happy at high temperature. This is when you put cholesterol in there. You see much less degrees of freedom, and then you can also have a quench through a phase transition, and you get to this scale. In all 3 phases, we see for different alpha values exactly this anti-persistent motion, but in the simplest case here, where everything has the same chemistry, we have crossovers at very short time scales. After 10 nanoseconds, there's a crossover. And in some cases, it goes to normal diffusion. In other cases, it's still subdiffusion, but with a larger exposure. And this is what we can describe by cutting off the power laws. So I have this power law here in the correlation function, and we can here now put a cutoff, a temporary. We can either use a steeper power law, and then we can still get subdiffusion afterwards, just with a larger alpha, or we can put, let's say, an exponential cutoff, and then we get convergence to normal Brownian motion. And when you look at these black lines, and I put them on top of the data, you see, of course, that's how they're constructed. They fit short and long time asymptotes, but I can't tell you for sure why the crossover fits so nicely. So it just turns out that even the crossover is beautifully described by this. But now let's see what happens when we introduce a bit of disorder in the system. So now this is a top view of these lipid bilayers. These are those lipid molecules. And now we put these big chunky pieces in there. These are membrane proteins. So they occur naturally. It's their natural environment. And we can look at the dilute limit, or when we crowd the membrane with these proteins. And what we see is I fit these data with what I call a stretched or compressed Gaussian. Of course, if this delta variable here were 2, it would be Gaussian. And what we see in the data is clearly the delta is below 2. There's a lot of data where people measure non-Gaussianity. Typically, they see exponential tails. In this case, we actually get something between a Gaussian and an exponential. You have a question?
How is this image generated?
This is just from simulations. They have all these beautiful fancy tools. That's why I love collaborating with all these simulators. I mean, come on, it was so aesthetic, all these pictures. Okay, so this is what we see, and in these plots, I should have said I plot 1 minus the cumulative, and then the log versus log r squared. So this makes up exactly the power law in here. Good. So how can we understand what happens here? And of course, when a lipid gets trapped in between those chunky pieces, it has a lower mobility, and that's what we also see in the data here. This is for the dilute case for 2 lipids. You see it looks pretty stationary, it looks just like fluctuating, and the statistic of the apparent diffusion coefficient is very narrow. Once we're in the dilute case, the crowded case, the fluctuations become much higher, and we also see some intermittent behavior when we see a much lower diffusivity. And this affects the very broad distribution of the diffusivity. Two peaks here, that's just a bit of fantasy, I would say, but you see it's very good. And a lot of these effects can be modeled simply by using a much simpler system, an argon gas, 2-dimensional argon gas, where here you have mobile argon particles, and these black chunky things, these are immobile clusters of argon. So you see the argon particles can be very mobile in the bulk, but when they have to go through this little narrow channel, of course, their mobility is much lower. So this reproduces a lot of this data. You also see that when you're in the dilute limit, you don't see any variation in the amplitude of the mean square displacement, but when you go to the crowded limit, you see a lot of variation in the amplitude, lots of heterogeneity in the motion. It's important for real cells. In the simulations, we can't get to these timescales, but when you look at real cells in the membranes, you see exponential tails for the displacement distribution at macroscopic times over many seconds and even minutes in those days. So we try to understand how does the Gaussianity vanish from fractional Brownian motion? How does how is it being converted to this non-Gaussianity? And I show you 2 little motivation pieces for this. One is look at what happens when you have a protein, a relatively simple, so-called mini protein in just water. This is a protein that only consists of very few amino acids, and it can assume many different configurations. It can be very compact, small hydration radius, it can be very extended, and of course it's bigger. And when we look at the time local diffusion exponents, to the top we have the gyration radius, the side, to the bottom we have the diffusion coefficient, then you see that they're perfectly anti-correlated. The bigger it is, the slower it is. So here we have an example how we can easily understand a stochastic diffusion coefficient. As function of time, the diffusivity varies stochastically. That's an example of very nice spectrum. Then this paper where they look at an environment like a gel, a hydrogel that is breathing. So when you have a particle moving through there, then you have areas that are less dense, more dense, and on their way, the particles will also have this stochastic diffusivity. So this is actually a model that was introduced for Brownian yet non-Gaussian motion several years ago, originally by my old colleague from Ottawa, Gary Slater, and then we published also several papers on this. And now we wanted to look at what happens when we use this for fractional Brownian motion. When you go to the Brownian case, there are many different, I didn't even list, I mean, there's a whole zoo of different approaches, how you formulate this model, but the behavior is very robust. No matter which model you use, the behavior is essentially the same, up to small b. Once we introduce the memory here, correlations, this is no longer the case. And that's actually, in that sense, a disappointing story that I tell you on this slide. Next. So we use the normal Langevin equation that I showed you before. I should scream too much. But now I have this stochastically varying amplitude, the noise, the diffusion coefficient in this thing. We wanted to have the this dynamic of the diffusion coefficient and the stationary process. So we use the squared Ornstein-Uhlenbeck for it squared. Of course, diffusivity has to be positive, but we want to avoid introducing a reflecting boundary. So this was actually our formulation. And we can calculate analytically limiting cases, but not the whole solution. This only works for the Brown. But in this, I should also have said here that the noise eta in the Ornstein-Uhlenbeck, that's like Gaussian, whereas here in the parental process, this is of course fractional Gaussian noise correlation. And I just show you the results. In all the cases we see, so we applied to 3 different models that look at non-Gaussian diffusion. In all the cases, we see a crossover at short times from an exponential tail. And then once you get across the time scale, here is 1 in this notation, but you have a correlation time in the Ornstein-Uhlenbeck process. And once you get beyond the correlation time, you see a crossover to Gaussian diffusion. That's essentially what you see in many of the experiments that you have crossovers. Many of the other models cannot describe the crossover. But once we now look at the behavior of the mean square displacement, you see already different. Depending on which exact model you choose, I will not dwell onto these. I just go to the one that's a generalization of the diffusing diffusivity model. You see that super diffusive motion stays super diffusive, subdiffusive becomes normal diffusive. And that's exactly what I said before. Due to this variation of the diffusivity, you break the property that the area under the noise correlate under the noise correlator is zero. And then you relax the model. We also get strange behaviors of the effective diffusion coefficient as functional of H. There's discontinuity. So that's where we are. We can model it. We can get something that crosses over from exponential to Gaussian. We can generalize this to non-exponential tails. This just changes the differential equation a bit. But what I don't like about this is the non-robustness, that the details of the model actually feed into the results. That's where we are. We call this a Prosecco, and that's an indication that this is worked out with our predictive power. And Prosecco this is the start. This is the simplest case. And we have in the back of our mind, we have a Vino model and we have a Grappa. So these are more complicated models, but we haven't got them. But one final word to this part of the talk. How much time?
7, no, 10 minutes.
Anyway, I should say that all these processes that we define, like fractional Brownian motion or others, for typical complex data, one of them is not enough. Many times you see crossovers. At shorter times, it's more like this process. At longer time, like another process. Even a very, very simple case, you more or less have a stiff drug molecule in between two glass surfaces, and we see power law waiting times. We see correlation functions like for fractional Brownian motion. We see non-ergodicity and whatnot. So it can be very complex, and of course we try to understand. Now, this is a picture of my hometown. This is probably more than 100 years ago. I grew up in this little house here, and this reminded me a lot of your landscapes yesterday. But especially I want to allude to the fact that in my hometown there's always a slope upwards. So let's quickly look at fractional Brownian motion in the external potential. Before I go there, one small slide on Levy flights, Markovian processes with long range, long tail jump length distributions. And here we see that if we have a potential that's steeper than harmonic, for harmonic, it stays a very stable student. That's gets the stationary limit. Once you go to steeper potentials, like quantic potential, you actually get a binodal distribution. That's one of the things I want you to remember. And if we go to shallower potentials, shallower than harmonic, then there's actually a crossover where you have a critical value of the scaling exponent of the stable law when it is no longer confined. So you have this escape, and I'll come back after this. Now let's go back to the fractional Brownian motion. And we see that when we go to a quantic potential, again, we have deviations from what we would expect. I mean, it's a nice simple potential. In the harmonic case, fractional Brownian motion, we heard always stays Gaussian. But once we go to the quantic potential, and here I have a super diffuser, the persistent FBM, we start before it feels the flanks of the potential, still Gaussian, but then when it relaxes and it really feels the wings of the potential, we see the bimodality. So that's a very, very strange feature of this fractional Brownian motion. And here, of course, it's you come, you're persistent, you bang into the boundary, you're reflecting, you still want to go this way. And this is why we have this accumulation of probability. And also in this case, I will not show you examples. Also, when we go to super diffusion of shallower potentials, we have the same behavior. The fractional Brownian motion can break out and still disperse to infinity, and actually get the same law for a critical exponent of the potential with respect to the self-similarity index of the motion. So this is a very strong similarity between fractional Brownian motion and Levy-Florence. Here you see a hard box, hard borders. This is subdiffusion. Here you get a depletion. Here the probability density goes down. This is super diffusion. Here the probability density goes down. And in the trajectories, Brownian motion in the box, that looks familiar. For subdiffusion, you see the walk avoids the boundaries. And for super diffusion, it's through to the boundary. And I don't know, this is something, yesterday I got this idea when we were talking fractal dimensions and whatnot. So I don't know whether this is changing something with the local fractal dimension when you go into these areas. I mean, this is something I'd really like to follow. Good. No. Why do we look at this very quick slide? I have friends in Santa Barbara, Stellantis, that have shown us this is how the whole thing about looking at boundary values came across. They are interested in densities of brain fibers, and what they see is that these fibers accumulate next to the hard boundaries of the skull. This is the mouse brain, so we're using, instead of having a random walk model for a Gaussian chain, we now use a persistent random walk model, a fractional Brownian motion that's persistent to model these growing fibers. This is very empirical, but we can actually reproduce a lot of what we see, even the details of how the fibers are grown. This is 2D, this is 3D. 3 more minutes? Yeah? Fine. Okay, good. I can continue to negotiate. The final point I want to make is very recent, and this is that people are trying to fiddle around with what happens when we don't have the same burst exponent during the entire motion or from one particle to the next. So there's several models now saying if Federal has something, Alexei Chechkin and our Polish friends have a paper where they use random burst exponents from one trajectory to the next. Now we're also trying to look at what happens when you have a stochastic growth of the scale of the Hurst exponent, but here I want to allude to a deterministic change in age. And this can happen when you look at time series of financial data, for instance, over many years. You see that this is not just stochastic, there's some determinism in here. It's connected crises, whatnot. Or when you look at what happens in the cytoskeleton cells, it's getting denser as function of time. So then we looked at what the mathematicians do to model these things. This is what they call multifractional Brownian motion. And it's perfect for their purposes because they're only interested in the roughness, meaning the increment of the process. How rough is the financial data at one point? But for physicists, it doesn't really work, and I'll show you why. So they use, first of all, the zero view. This is the definition that Levy gave for fractional Brownian motion. Mandelbrot then used minus infinity. And so this is actually good for a physical process that we started and initiated that frequency. But then let's see, here we have our Brownian motion, that's the beta process, and then we have these memory kernels. And if alpha were constant, this would just be the Levy fractional Brownian motion. But now they introduce an alpha of 2. But you see, inside the integral, it doesn't vary with the integration variable. So when you evaluate your mean square displacement at any moment is alpha of t. There's no memory of what was going on before. No matter what your protocol for alpha is, always very small, all of a sudden big, or the opposite, you don't see. So this definition is lacking something. And for instance, if we want to look at a diffusion process that has a time varying diffusion coefficient, this is how we can write it. So we have the memory of the process, we just combine increments with given diffusivity over time. And for instance, when I switch diffusivity, that's what I get. When I switch from one value to another, of course, I expect that I remember what was there before, how far the particle managed to go before. And this is now what I also want to introduce in the what I call memory multifractional Brownian motion. Here it's no longer alpha of t, now it's alpha of s. And that has all kinds of beautiful properties. First of all, the motion is now continuous. When you use the old definition, there's jumps in trajectories. In our version, it's continuous. You see the process is really continuous. And we also have the memories. So for instance, when we switch with specific values from alpha 1 to alpha 2, you see that we get a combination of scaling experiments. And for instance, we get a new scaling regime. When we really take the memory into account, it can dominate also the long-term motion of a particle. And that's, I think, something that is quite attractive for modeling. We still need to look at it in more detail. Yes.
If you are interested in modeling crisis,
yes,
related thing, maybe discontinuities would be advantageous rather than like having a continuous process, right?
It depends what you want to look at. For me, I'm a physicist. I want to look at a particle that cannot be transported in space in an instant. So I expect things to be continuous. That's my requirement for the process. And then we end up here. I think also when you look at cumulative properties of financial data, you will need this generalization because the other process does not remember anything. It always treats your process with the alpha that's given there.
But it also depends on the function alpha, right? So because like if your alpha t minus epsilon is big, you can create a function that it's going to like go down like
yes, but you still have the property that the old definition, let's say a mean square displacement or cumulative property, would always depend on your now value. It would not remember the past. That's kind of the point I want to. Good. Very quick flash out.
One more minute.
Yes, I'll be there.
That's right.
So we also work a lot on data assimilation recently, and 2 years ago we launched the Anomalous Diffusion Challenge with friends from Barcelona. So we gave data time series on the internet. People could analyze them, let us know which anomalous diffusion processes behind continuous time random walk, fractional Brownian motion. What are the parameters and so on? So this was published 2 years ago. Now we're launching the new Andy challenge. So watch out if you want to analyze data, it will be much more difficult now. And the other thing I wanted to show, this is work I did with my PhD student Henrik recently, when we want to ask how can we add some kind of reliability to a machine learning analysis of stochastic data. So now there's a multi-swag Bayesian analysis on top of the machine learning that gives you all kinds of confidence intervals. Whether the machine learning is actually even meaningful for this kind of data, whether you should believe the result or not. You will find my email address on the internet. I can gladly send you the slides. So I showed you the non-Gaussianity with the fractional Brownian motion. I showed you the interaction with the external potential. And in all cases, fractional Brownian motion is not a nice process. I mean, it's beautiful, it's simple in definition, but calculating things, try to calculate the first passage behavior is one of the hard problems, right? It's not a nice process. So there's always another surprise. As a local, and now I will use 1 more minute, I'm sorry. As a local, I grew up not very far from here, so I feel I should say a word about the University of Tübingen for your benefit. So it was founded quite early. I think it was the 7th university in Germany, was founded by the local rulers, and I love the motto. The motto he gave it was attempt to idea. He just came back from a cruise, from a pilgrimage to Jerusalem, so this is why you have the palm tree as the symbol of the university now. And these are just a few examples of people who studied here. Kepler is my local hero. He's from not far from here, but you see all kinds of very famous people were here. So you should also enjoy this part of why we're in Tübingen. It's not just a nice place, it's also a pretty good university. Thanks.
Yeah. Yeah. We want to start? No.
I'm really scared of asking a very stupid question, but I will go ahead.